Hello, everyone. My name is Spencer Sevilla. I'm a researcher at the University of Washington, and I'm here to talk to you about challenges and opportunities in community cellular networks. So first off, a bit about myself. My background, I'm from California, did my undergrad at Davis. I am a banana slug, did my PhD at UC Santa Cruz, where I worked with JJ Garcia Luna Aceves. During this time, I worked mostly on network architecture, mobile networks routing, and then from there, I moved to where I currently live in Seattle, where I work at the University of Washington. This talk, I'm going to start off with a little bit of information just broadly of the field I work in, which is to say global internet access, expanding it. And then from there, I'm going to give you a brief rundown of cellular network architecture and how it relates to open source. We'll talk more specifically about the community cellular networks that I build and maintain, and then we'll wrap up with kind of future research directions and interesting open questions in the space. So first off, this is a kind of color-coded map of internet penetration rates per country per 2017. The numbers have slightly changed, but they're still relatively current. If you dig down, you should not be surprised. You can see Canada's up at 91, US 75. And then as you get kind of less developed, you start seeing lower numbers. You kind of expect this. Somalia is a kind of particularly low outlier here at 1.9%. I believe there's a lot more unrest in the country at the moment of this taking. So when we talk about global internet access, there's just general access and there's also broadband access. And both of these, there's two main trends that you can see. The first trend is that the numbers keep going up, more humans keep coming online. This map says we're just around 55% online, which, the implication is that now we have 45% of the population has no internet access whatsoever. But what's equally important is if you look at this rate of change, it's starting to slow and it's really starting to taper off almost to what some people are worried is going to be almost an asymptotic slowdown. And if you look into kind of why this is, a lot of people are talking about it. And the question is, even since 2016, the GSMA is saying that, look, we have rolled out coverage as far as we possibly can. We have reached the terrain coverage and the human coverage that we're going to do it. And we just can't be commercially sustainable otherwise. So this kind of makes sense. And then you look at the actual numbers and we're talking 3.5 billion humans without any broadband access. And like we mentioned before, the growth is slowing. And then we also have 800 million people without any access. And this is including cellular phones, any sort of telephony, any sort of communication whatsoever. We have almost a billion humans, and this growth has widely stopped. So who has access and why? I showed you a chart with kind of this developed world by country breakdown. And yes, the split is real, but it's far less impactful than a rural-urban split, which is to say urban areas are densely connected and becoming more connected, and rural areas are continuing to be left behind and not seeing investment. You can even focus in the United States. We have 96% of urban Americans have access to broadband. That number drops to 60% of rural Americans, and to intersect it with race a little bit, 30% of tribal Americans. So these numbers are dismal and they're largely stagnant. And there's a question of why. Well, let's do something about this. What are the barriers? And they are many, but as I mentioned earlier with the GSMA quote, these barriers are largely financial. CapEx is higher because you're talking big satellite dishes, solar panels for off-grid powering of these towers. Trenching fiber hundreds of miles doesn't work. And when you do finally build these towers, you see an increased failure rate, you have increased travel times for your technicians to repair these areas. Meanwhile, you have a market failure, lower population density, often lower income users. So all this sums up to say the cost is too high, the revenue is too low, it's basic economics. So what do we do about that? There's a couple of popular approaches. One of the first ones is public investment, which is to say there's many universal service fund approaches, which are basically a way in which the government pays the incumbents in the United States. In the United States case, it's mostly Verizon, to say, hey, if you're operating at a loss, we'll pick up the tab. We want these humans to have access. And that's one way to go about it. But there are obviously problems. First and foremost being, this is driving centralization and control. No small players can get into this game. You have to be huge to cut a deal like this with a national government. It's also very expensive. And one of the main reasons why is, we mentioned that these areas are largely considered to be financial kind of losses. They're poor investments from the perspective of a telco. So they have not architected for this. They don't think in terms of solar panels. They don't think in terms of off-grid trucks. There's a lot of knock-on effects that they just are not interested in this. They're much more interested in trucks that can easily spin out 5G coverage out of vans here in a place like Seattle. So this is expensive. It's not what telcos want to do, but also this is not a political talk, and I'm not here to advocate for public investment. This is just one option. Approach number two is private investment, which is to say, many times in the news, you read headlines of Facebook and Google spinning up connectivity projects, balloons, drones. There's lots of other kind of wacky solutions. Low Earth orbit satellites are getting a lot of headlines right now. And the key economic innovation here is these companies can somehow monetize their users, right? Whether it's you're going to be on Facebook, you're going to be using Google. This is more data, more ad eyeballs. It's worth it to us to connect you just so you can go to our website. But there are some drawbacks here as well. First and foremost, it tends to drive a surveillance economy that's based on ad revenue. It continues to drive vertical stack integration and monopolistic control. Often this is because now you're talking about the same companies controlling the physical infrastructure as well as the services on top. Oftentimes because of this, you see pretty widespread news of violations of good internet practices, whether it's running your own routing protocols that you're not interconnecting with BGP, whether it's violating net neutrality. Free Basics often gets in trouble for this. You have free internet, but only to Facebook, so on and so forth. But if you look at these projects over a long term, you also see that they often get spun up and then shut down. And the reason why is oftentimes it's unclear if the ad revenue model actually works. When you're talking about people in a really underserved area that are oftentimes subsistence farmers getting by on the severe poverty line, a handful of dollars a day, no matter how many ads you show them, they're probably not going to buy enough to eventually make it worthwhile, and so on and so forth. So you're trying to kind of monetize users that don't have any money to monetize, regardless of if you could convince them to give it to you or not. So these projects often get spun up and then they kind of get shuttered, and they kind of work, they kind of don't, but this is not the trajectory for long-lasting change. And then there's a third, lesser known approach that is what I work and advocate for, which is essentially local investment. I work in the field of what are called community networks, which are networks bought, built, owned, and operated by local actors. And there's a lot of reasons why you can do this. First and foremost, people in disconnected areas are highly incentivized to get themselves online. So they're here saying, even if it's expensive, we want to do it. And oftentimes this goes hand in hand with affordability, which is to say, community networks often have kind of an amateur hour feel that lets them operate at a far lower cost. Most telcos, in their budgets for installing a new cellular tower, this can run $1 million. This is a picture of my friend Shadi in Mexico. That is clearly not a $1 million tower, but it works. And the third reason, which I hope that this crowd will appreciate in an open source software symposium, is that a DIY local ethic is the classic internet design. It's how it was built. It's how open source tools are built and maintained. It is every geek in the room should be saying, yeah, this looks like fun, and it is. Okay, so there's a handful of well-known community networks. One of the most famous is Guifi. There's about 35,000 nodes. It operates mostly over Catalonia in Europe, just a big rural area that has poor connectivity. It was started by a frustrated retired engineer and now has grown quite large. The second most popular one in the United States right now is called NYC Mesh. They work obviously in a very urban area, and they focus on underserved buildings, oftentimes specifically buildings in low-income areas are passed by with broadband. So they work mostly on income inequality in terms of access. They have approximately 250 nodes, somewhere in there. They're very quickly growing. I urge you to check them out. They're fascinating and very fun people. But when you look at the hardware, when you start talking to community networks, what you'll find is it's very much a lot of the same gear. It's long distance wireless links. They're usually unlicensed in 5 gigahertz. You create like a point-to-point mesh, and then you have Wi-Fi access points that your users connect to the network with. There's some pretty common hardware choices. Ubiquiti and MikroTik are common. The ecosystem is kind of matured. It used to be really janky. Now the open source software packages like OpenWRT tend to work pretty well. But very conspicuously absent from the community networking space are anything related to cellular technologies. It's almost always unlicensed mesh networks with Wi-Fi as the access. So I'm here to talk about community cellular. And to start, we have to talk about cellular networks in general. So first off, we're gonna backtrack a little bit to the publicly switched telephone network. SS7 has been in use since 1975, is the signaling protocol used. And we're connecting, you can think of a contiguous copper circuit from one handset all the way through the network to the other one. It's a physical circuit, it's not even a virtual one. This is important because when we talk about the first generation of cellular networks, they were single hop extensions to this PSTN. So you have a copper circuit from one handset all the way to the correct radio tower. From there, it's just a wireless link to the handset device. Everything else is in copper. It was essentially physically switched. And as a result, when we talk about open source disruption, can we innovate here on the first gen of cellular networks? We cannot, because there's not even software. But obviously cellular networks are complicated beasts, and really quickly we moved from 1G up into 2G. And so with 2G networks, it was the kind of the rise of nationwide cellular networks. They focused on cellular coverage as a principal service. They still have dedicated physical channels. One call takes about 200 kilohertz of spectrum. If you just want to do some math, figure out how many calls a tower can run simultaneously. But they also started adding cellular-only features. They started adding SMS. They started adding network mobility, all these star codes, USSD. These phones can actually do lots of things that aren't even that well known. But because of all this, we're talking about a rise in complexity, and with it actually became the rise of software in cellular networks. So this ugly, complicated diagram is a 2G network. There are 11 different software components that do various random things. They are all needed to run your basic network. There are optional components as well. This is the most basic 2G network you can build, is this diagram. It's ugly and it's obnoxious. But it still is software. So can we open source the software? Well, of course we can. Just grab an SDR, start collecting traces off the wire, start reverse engineering the spec. And a man named Harold Welty, who was working on Linux for a long time before this, decided to start doing this. And Harold's goal was to build an open source 2G network technology. And he immediately ran into a large number of roadblocks. The first of which are that patents essentially abound in the 2G space. There are patents in the base station design, which means that it's impossible to build a base station, a 2G base station, without paying a lot of licensing fees. But even when you get around this, there are patents in the interface specifications themselves. These patents exist. So if you look at this code snippet right here, this is copied directly off of Osmocom's code. You try to run a 2G network, you find that there's a crash. I start following the trace, I start examining the code, what's happening, and I eventually find a function that looks like this, which is totally just, it's sending reject updates here. You can see it at the bottom, and it's unimplemented due to legal concerns. So how do you get around this? How do you build a working network, right? When you can't even write the open source code. So solution one is you can license the patents, which is prohibitively expensive. Solution two is you can wait for the patents to expire, which often takes a very long time depending on where they were filed. Solution three, which is actually quite common, is you can write your software in France where there are no software patents and you're protected, but there are issues if you put this code on GitHub, so on and so forth. I'm not an IP lawyer, so don't follow this advice without consulting someone else. Or solution four is you can just kind of do it. This is not an admission of guilt, but this is a known practice that some people can choose to write code. So say you get past the patents and you're excited to write your 2G network. The next thing that you will find when you're trying to build an excellent compliant 2G network is that the 2G spec in a couple of key places contradicts itself. This has to do with certain edge cases that weren't handled, in the sense of you send a message, there's no response, you wait for a timeout. Meanwhile, another part of the spec is saying that you should send a reject, another one's saying you should drop it, so on and so forth. So this is a huge problem for building a robust, reliable network for obvious reasons. And even worse, it means that every base station manufacturer has to make assumptions just to go one way or the other in order to proceed. So you're a base station manufacturer, you make your assumptions, you want it to be compatible, so you also sell a license to the software packages that you develop. This kills hardware-software compatibility, means that you're kind of locked into a vendor's software and their hardware. There's no really good solutions here, unfortunately. As good as it gets is the Osmocom folks also started building their own base stations. This is the OpenBTS project, saying our software works with our hardware just the same as every other manufacturer. Or the other approach you can use is compile time macros to say, here's our open source 2G stack, and when you compile it, just specify what your assumptions are or what base station you're trying to build and run against. But obviously this is a significant roadblock towards just a robust standard engineered software package the way you or I might think of running on top of an x86 machine, for example. The final challenge is that 2G spectrum is very strictly licensed. All 2G networks run in just one of 4 bands, 850, 900, 1800, or 1900 megahertz. And because these networks are tightly controlled and centralized, they don't have the unlicensed things such as collision detection, collision avoidance, all the things that make Wi-Fi just kind of robust and work. Unfortunately, the lack of these things means that no spectral reuse is really possible. As a result, these bands are usually occupied. These bands are usually bought and owned nationwide. And if you want to buy one of these bands, they usually go for billions of dollars US. So you can't legally run it without one of these licenses. The handsets are only going to run in these 4 bands, so you can't just hack them to run in some unlicensed band or something. And this is a significant roadblock for building up a 2G network. More on this later. Let's say you've got a Spectrum license and you've got your open source stack, you've got your base station, you've got your phone. How do you get a phone number? And if you could kind of make one up if you're running your own network, but how do you interconnect it with the rest of the phone network? The answer is we actually have basically almost no idea. There's no standardized body. This whole process is somewhat opaque. There's no organization you can apply to and say, I want some numbers. It's very, very hard for small organizations. A lot of the phone number interconnect and routing happened kind of organically as almost gentlemen's agreements between operators, so that the mappings of what numbers go to what network is not standardized. This process is a humongous headache, and there's a lot of things here in the cellular space, this being big one of them, where you might say that design sounds absurd, and the answer is yes, and we did it better with IP. So there's a lot of things when you go backwards almost when you're engineering, when you're used to network engineering and you move over to cellular, you find a lot of problems like this where you say, how is this still running? And they say, I don't know, it just is. So last thing that I want to talk about in kind of the 2G, 3G space is the main shortcoming of 2G, in addition to everything I've just listed, in terms of user perspective, is you have pretty much no internet access. Technically, there's a technology called GPRS that can get you 20 kilobits per second, but you have to think in terms of a telecom operator circa 2006 or so, how can we add internet to our existing 2G network? And the answer is just like the good old days, think about it in a dial-up context. So it's not using the audio channel the way an old 56K modem is, but it is using a very similar architecture. And this is what 3G is. You take an internet gateway, you slap it somewhere in the network. When your phone wants to use data, your phone sets up a data channel over the physical circuit to this gateway and just sends IP traffic this way. And in case any of you remember or noticed this in the 3G world, you cannot use the internet and be on a voice call at the same time because it's using the same channel. This is why it's exactly the same as back in the 90s when you'd be on the dial-up and someone picks up the phone and your download disconnects and you have a nice argument over it in the family. So we have all these things where the nice thing about 2G and 3G is we're in the software space, but the risk of open source disruption and innovation is slightly better, but still not that great. Yeah, we have software now, so we can open source it, but we have issues around hardware. We have issues of conflicts in the spec. We have spectrum access issues. Phone number and interconnect is almost impossible. So we've got a handful of serious problems here to just picking it up, running with it, and building your own phone network in your backyard. But innovation goes on, thankfully, and if we fast forward a bit more to 2010, by now, we're well aware of all the problems I've listed. The spec conflicts have been argued to death, they've been hammered out, and so we know these problems, and at the same time, we're also seeing a huge rise in internet traffic. Voice calls are so low bandwidth by comparison that you build the 3G network and it's immediately swamped with data. And because, again, these 3G networks relied on these gateways, they're starting to see a scalability problem. And also running all your datagrams on top of these physical circuits through your network to this small number of gateways is, from a network engineering perspective, a pretty stupid way to architect your network, especially when internet traffic is now just dominating your throughput, your network traffic. So if you want to build a high-performing network, packet switching scales far better than circuit switching. This was the argument since the 70s. The modern internet has widely borne this out to be true. So let's rethink things from the ground up. Let's rewrite the cellular network. Let's redesign it to put IP traffic first, and we'll build it for long-term evolution. And now we're talking about LTE. So this is a diagram of an LTE network. And the first thing I want you all to understand is that it is much simpler than a 2G network. The three components on the right, the HSS, MME, and SPGW, are the three software packages. The eNode B is the base station, and then there's the phone. In terms of breaking down these logical components, the HSS stores all the subscriber data. The MME handles all the control plane signaling, specifically with respect to mobility. And the SPGW is simply the gateway that forwards traffic, in this case to the internet. And you can interconnect an LTE network with a 2G network because you want to kind of have seamless rollover and things like that. And so aside from the subscriber information, which needs to be kept consistent at the HSS, we're taking all this 2G mess and we're just pointing an arrow saying it's over there, there's an interface. We really don't want to intersect with it anymore because it's too complicated. So moving even further, we threw out all that complicated 2G stuff. We're running with a much cleaner LTE network at this point, and we're going to base the whole thing on IP. Every entity has an IP address. This includes phones. The first thing they do when they bootstrap is to get an IP address. The entire network is packet switched. And we didn't forget about voice and text. We're just going to throw them on top of IP addresses as well. So VoLTE, voice over LTE, is simply SIP and VoIP. Calls just have some network provided QoS, and I'll talk about quality of service a bit more later. And SMS is just handled over UDP. It's send a message to this IP address, great, you're done. And here's our LTE network. Oh, we want to add voice to it. We'll just connect a VoIP server somewhere in the network and tell phones, there's your VoIP server, go route your calls. So this is starting to look good. It can scale well. It's simple. You can add things to it in a way that makes sense. And we're starting to feel a bit more like this is a normal network. This is a normal thing that a modern software engineer would build. Even further, we're solving problems with 2G. So when we talk about base stations, we have a cleanly defined spec. We don't have contradictions anymore. We specifically designed the base station technologies that were standardized to not be patent encumbered. And because of these two factors, small hardware manufacturers can start up and get into the game. Any manufacturer can say, I'm going to build a base station that is fully compliant, and it can be almost plug and play with other base stations. As a result, you introduce competition into the space, and as a result, you see we have a world today in which the LTE base station is almost a third the cost and dropping of a traditional 2G base station. It does a lot more for a lot less, just because you can introduce innovation and you don't have this lock-in, you don't have the patent expenses that I mentioned earlier. So again, this space is starting to disrupt. It's starting to feel good. Commodity hardware, and more vendors getting into the game. This is continuing to look good. And so, but when we go to the core network, we don't see that yet. When we talk about those software packages, the HSS, MME, SPGW, they're software that can run on x86 computers. This is great. But the commercial packages, there's very little competition in this space. And one of the lower quotes you can get for installing and maintaining all the core software to run an LTE network was approximately $5 million, give or take $1 million. So this is incredibly high cost to starting up a network. We're so excited about these cheap hardware packages, and we're just getting killed on the software side. But if the code is clean, we can write it as spec compliant. And if we have all these different small hardware manufacturers that we can connect with, we're starting to see an actual risk of open source disruption and innovation. So again, user space code, commodity hardware interoperability at a clean spec. And then because we're based on IP packets, interconnect gets a bazillion times easier than all this PSTN stuff I talked about earlier. So this was broadly the space when we started working, and I'll tell you a little bit more about what we built. But in this way, we're going to return back to global internet access. And specifically, this is a story involving two nonprofits that we work with on opposite ends of the globe. There's Rhizomatica on the left that works in southern Mexico, and then there's Airwave Missions on the right, which works in Papua. And both of them came up with a similar goal in the early to mid 2010s, which was to say, using open source software and hardware to set up a low-cost cell network and use this to see if we can connect these previously disconnected populations I was mentioning earlier. So how do we do this, right? Let's break it down into a handful of steps. Step one is to go ahead and buy the base stations. And actually, there's lots of grants to do this. So, and this is the least expensive part of the project. So done, we've picked up our base stations. The rest of these steps get a bit more complicated. We got to have access to spectrum. We need to figure out some phone numbers. How are we going to do interconnect with the world? How are we physically going to connect these networks to the rest of the world with backhaul? And then step 5, because it's actually non-trivial, is how are we going to get SIM cards? How are we going to actually set up this thing so that people can use this network with their phones? So first, I'm going to kind of run you through spectrum. There's an obvious tautology here, in which is spectrum not in use. Spectrum in uncovered areas is not in use. So how can we gain access to these bands? Oftentimes, they're still owned, they're still licensed, they're just fallow. And there's a handful of solutions here. If you know someone at a telco, oftentimes they're kind of interested in, oh, you know, that's cute. We're not helping anyone in those tribal areas. Sure, use it. So you can get a license exemption. Solution 2 is if you know someone at the regulatory body, you can ask them and you can tell them a sob story about disconnected populations. And oftentimes the regulator will lean on an owner or write you out some specific kind of corner case license that lets you operate. Solution 3 is you can lean on the fact that you're a research institution, if you are one, and use this to kind of get a special research license or otherwise push on a regulator this way. Or the fourth solution is you can just do it. You can just say, there's no coverage here, we're not going to interfere. I'm not worried about someone coming into this area anytime soon, and you can just turn on a base station. We have tried all 4 of these solutions at various points in our work. So you figured out a solution to spectrum, either by hook or by crook. And the next task to work on is phone numbers and interconnect, because again, you need a phone number to call something. And we've seen a variety of kind of fun approaches here as well. The first solution that we've seen is networks patch calls out using Skype. They built kind of a Skype gateway. You, as a phone, you place a call in the network, it routes it out via Skype. The primary drawback of this design is that it doesn't allow inbound calls because no one actually has a valid PSTN number. They simply are calling from a Skype account. So this is really similar to NAT and has the same set of drawbacks. In one area, they actually built some phone tree software to allow inbound calls. You call a number and then you kind of, enter the extension, press pound. This still doesn't work with SMS for obvious reasons. There's no way to SMS to such a number. But this is one way that you can actually have calling in and out. It's essentially NAT hole punching and then NAT traversal. The second set of solution is Twilio owns a large number of phone numbers. They handle the interconnect, and you can buy numbers from them with a monthly fee. If you try to do this, you'll quickly find that Swedish numbers are the cheapest numbers. We have no idea why this is the case. And so we did this in Papua. So we bought a Swedish set of numbers on Twilio, we hooked them up. It works fine locally. I think you can kind of get around international calling if they're calling other people in their real country by virtue of the way Twilio does the routing. But there is one specific bug / feature, which is if you misdial, you are immediately connected to another person on the other side of the world speaking a different language in the middle of their night. And so here we have a nice diagram of 2 young people having a meeting, discussing things with a misdial. There was always a hope that they would make friends, but this never happened. But there were definitely misdials in these networks. So the third solution that you can do is you can just forget about phone numbers interconnect. And if you're in the LTE space, you can run a network that's internet only. And you can just say over-the-top services, which are essentially Skype, WhatsApp, Messenger, services that do telecommunications just over the data channel as IP traffic. You can just punt to these services. You can say, hey, this actually works. Phones are fine with this. You can attach almost any phone to an LTE network, even if it doesn't have a phone number and it can't place voice calls. And this is actually kind of nice because in a lot of countries, WhatsApp is already the preference due to high costs, due to interconnect issues between carriers, so on and so forth. But there is a significant problem with this solution on its own in that almost every over-the-top telecom provider that we've seen needs a phone number to register using SMS for 2-factor authentication. So once you register, you can get off the network, but you can't get the WhatsApp until you already have SMS. It's kind of a chicken and the egg situation, but seems to work pretty well for us if users already had WhatsApp verified and installed. Okay, so now we've got a network. We're hammering through these issues, spectrum, interconnect, so on and so forth. The next thing you've got to think about is backhaul, which is how are you going to literally connect your network to the rest of the internet, the rest of the PSTN. There's a handful of solutions. The first one, which we use in Papua, is we use a geosynchronous satellite, a geostationary, excuse me. Satellite networks are nice in that they can work anywhere on Earth and they're relatively self-contained. You buy an account with a satellite provider, you install your dish, you angle it at the right place, and then it works. You only have one hop to maintain. The satellite network does the rest of the routing. But the primary problem with this approach is that it is both slow and expensive. By slow, I'm talking that pings to Papua routinely take over a second. And for this slow coverage, we pay $300 a month for 3 megabits. So this is latent, it's congested, it's incredibly expensive, and tends to dominate the cost of our network. So you get tired of satellites, you can also build your own long distance network. You can use multiple hops of like long distance wireless. So this picture is a repeater in a different area where it's taking information from one side, just relaying it and blasting it out to another direction. You can build up to however many hops of relays, but the more hops you put in, you start seeing significant performance degradations. And this also requires a fair amount of maintenance. Something that we've seen, especially in mountainous regions, is you'll see several wireless hops in order to go mountaintop to mountaintop and then down to a community, except these things get hit by lightning almost constantly. So you put them at the top of a mountain, it's got great coverage, and then it's fried. So there's a lot of maintenance involved and weatherization depending on exactly where you are. And there are issues when you chain too many of them together. But aside from these, you have higher bandwidth at a lower cost because this hardware is somewhat mature. You can build it for relatively cheap commodity hardware, and then you can see, pretty fat pipes. Last piece of hardware that we need to look into for running one of these networks is SIM cards. And SIM cards are fascinating. There's an entire talk I could give just on the SIM card architecture. These are these little smart cards that run actually applets. But anyways, to avoid these challenges, for here I can suffice to say that there's lots of different options. You need to choose the right ones, but there's tons of manufacturers in Alibaba that sell SIM cards. They're roughly 50 cents a SIM. You usually have to buy 1,000 or more. But the nice side is you can put your own design. So this picture are SIMs that we manufactured for the network that we support in Papua. This is a picture of one of their guys in the community. People love it. It builds home this community DIY ethic. We have our own SIM cards. We have our own network. People love it. It's an immediate selling point for the network. So we've kind of hammered through all these challenges, and now I'm going to talk a little bit about what we built, what we rolled out, what we operate, so on and so forth. So there's 2 networks that we work with. The first one is in southern Oaxaca, and they mostly do their own thing. We collaborate with them loosely for like technical innovation and research on and off. And they do an amazing job. They've been providing 2G only connectivity since about 2013. This is a group called Rhizomatica. They serve over 5,000 people now, usually indigenous folks in small pueblos outside of Oaxaca area. It's, I think, over 20 sites that they have. We've been working towards integrating LTE into these networks. There's a number of roadblocks that we've been chiseling through and figuring out how we integrate with their management tools, how we actually build an open source LTE network that interfaces with 2G, so on and so forth. This is ongoing work. They're also waiting on a spectrum license before they start spinning up LTE, I believe. On the other side, in Papua, this is an internet-only LTE network that we have been running since 2018. This is a picture of myself, grad student Matt Johnson, and Mr. Ebel, who is the man of all trades who helps us on the ground in Papua. We spun this network up in July of 2018. There's over 600 people that are our active customers on this network sharing their 3 megabits. And I personally designed, built, and now support and manage this network from where I live back in Seattle. So we're going to start telling you a bit more about what we built for this specific network in Papua, this LTE-only network. To build this, we came up with a software package called Kulti for just community LTE. And so we based it off of an open source LTE stack called Open5GS. We took it, we started stabilizing it, systemizing it, making it easy to install. We wrote config and management tools, so on and so forth. We, for a number of reasons that I'll be kind of getting to, this network only provides internet access, but it does go directly to handsets. And because we're researchers and also because we're a very small team, the main design principle that drove all of our engineering here was just keeping it incredibly simple. So to make this work, I actually had to kind of reimagine, re-architect some things in LTE. The first design principle that we were grabbing was embracing the dumb pipe. This is a pipe. It says you're the universe experiencing itself. It's dumb graffiti. But anyways, on the left side, we have this classic LTE that I've been talking about. There's telecom services and there's internet. There's voice, SMS, there's phone numbers, there's roaming, and all this stuff is expensive because, like I mentioned, it's hard to hook up. Our approach was disregard everything in the left box, throw it in the trash. It's complicated. I'm behind schedule. And we're just going to rely on over-the-top services. So we're going to take all this stuff and just punt it over to WhatsApp. And this half became as a way to save effort and make sure that we ship on time. And also was driven by the community itself, because we found ourselves hooking up internet access pretty quickly. I was struggling to add voice support. And in our calls with these network, in our calls with the folks in Papua, every time I'd tell them, hey, I'm still working on figuring out voice, it might take a while longer. And they'd say, yeah, can it do WhatsApp? And I would say, well, sure, it already does WhatsApp. And after the third time, they made it really clear that's all they cared about. I said, great, we're shipping, and this has actually worked astoundingly well. So the second design principle that we really tried to lean into was cellular security. And so when you look at classic LTE, you have there are symmetric keys. There's two symmetric keys stored on the SIM card that are used for bidirectional authentication. And these are very strong primitives. It's really hard. I don't think it's done yet for people to hack SIM cards to get the information off of them. This cryptographic validation during attach is very secure. And so we looked at these and we said, actually, these are great. So we've been talking about keeping it simple, designing an internet-only system, but this is way better than Wi-Fi. There's no passwords. There's no MAC. There's no captive portal. There's none of the stuff. There's no ARP spoofing or other classic Wi-Fi attacks because there's no ARP. It's simply you can uniquely identify users based on their IMSI, which is a SIM card, an identifier burned to the SIM card, and you have really strong security. You know that the handset is bound to this identity, and this lets us actually move really fast. The third design principle that wraps up kind of some of the changes we made is a simple and neutral billing system. So on the top design here is the design of all the billing components that are used in LTE. And there are essentially 6 or 7 different components. They're complicated. And the reason why is because when you start thinking about a fully fledged cellular network, there's a lot of moving parts. There's other networks with roaming. There's these weird custom promos. There's prepaid plans, postpaid plans, billing them separately. There's unlimited plans. There's service differentiation is actually a huge component here, which is to say it's VoIP. You make a VoIP call, so just packets are packets, but we need to bill these packets as minutes and we need to not bill them as data against your phone's plan. And so we said, none of this was built and we don't have time for this. So we threw it all in the trash and we simply said, I'm just gonna write up a tool. We wrote it kind of over a weekend. It's just gonna log bits. You have prepaid plans per megabyte. This is very simple. This is the only stuff you can buy. We don't do voice. If we did, we'd just bill it as bits. And this actually let us use a number of just standard system IP tools, net filter, IP tables, common system techniques that have been around for decades. What's actually really interesting is we built this because we were in such a rush. And then we sat back and said, actually, this is correct. This is simple. This makes more sense. And again, because we're able to rely on these link layer primitives, this IMSI identifier, we're able to say there's no passwords, there's no captive portals, there's no weird logins. Another interesting factor about this that I'm going to talk a little bit more later is this billing is also cleaner and arguably more net neutral, a lot fairer than the complicated telecom design instead, especially when it comes to differentiating minutes from bits. So we built all this and we ran it out. We installed a tower with 2 sectors on the top of the largest building in the town, which was a school, like a school building. And on the left, we have a map of the population centers. This is me making this map by walking around. On the right, we have coverage. This was me walking around, recording signal strength on my phone, the digital equivalent of the Can You Hear Me Now? And what you'll find is, first off, we cover almost all the population incredibly well. In addition, the network could cover even a lot farther. the drop-offs that you see in coverage in the green correspond roughly to elevation changes. In the bottom left, there's a huge hill that slopes up that kind of kills coverage, but no one lives there. In the top right side, you see there's a steep drop-off where a ravine, essentially, you go over a corner, it drops down into a ravine leading to the river, and that's where coverage ends as well. I was talking earlier about monetary access, and what we found is that we got the whole network off the ground for about $9,000. This cost was almost all hardware for these, mostly the base stations. Our OpEx is comprised completely of this incredibly expensive and slow satellite connection I mentioned earlier. We pay $300 a month for this. Power comes from the solar panels. This entire community lives off grid. They had a bit of excess power on their solar panels, so we get out the door for free. We don't pay rent because we're just using an existing community building and people like internet. And the revenue based on this is actually huge. We don't charge people very much. We tried to charge them something that we felt was quite low, and we still are making money almost hand over fist. This network has already paid for itself and is generating a large amount of economic activity in the community. But this is not a story about how I'm making a bunch of money by extracting it from these poor rural Papuans. The profit stays local and is reinvested into the local school and other community building programs. So to kind of wrap this up, there's a bunch of ongoing work here that we're doing in terms of ongoing engineering efforts. And the first is that we have seen a remarkable amount of heterogeneity in handsets. This is to say, there's a lot of handsets that don't follow the spec. You try to figure out which handsets they are, and the device identifier, the IMEI, is fake or unassigned. So there are weird device manufacturers that are just making up their IDs. They're not even spec compliant. And this trick, this is actually a significant problem for us because the centralized nature of the LTE architecture means that if they crash any of our core software, they have essentially crashed the entire network. And to be clear, when I say non-spec compliant, I mean sending joins on top of joins, sending a reject with a fake identifier that they just made up, tons of stuff that almost feel like attacks. And so our network is stable, but dealing with these wonky handsets has severely widened the attack space. And we spent an inordinate amount of time both figuring out what exactly the spec should be in various behavior, and then implementing it against an incredibly, a set of incredibly misbehaving handsets. But this brings me to the second an ongoing effort that we have, which is to say, working towards code hardening, and specifically with respect to increasing our uptime. So I mentioned that we're dealing with these non-compliant handsets, but there's a lot of edge cases where something can go wrong. And this is because the cellular signaling stack is far, far, far more complicated than Wi-Fi. There's all these things like voice calls, handovers, 2G to 4G, like rollback. There's a lot of different weird edge cases. It's a very complex written specification. And the crunch is that if you run a cellular network in the US, the FCC is pretty much mandating that cellular network providers provide 5 nines of uptime. So this is huge. This is taken very seriously. We do an all right job, but we are nowhere near 5 nines. We're actually down at 66%. The reason why is because our network is solar paneled and goes off every evening from about 9 p.m. to 6 a.m. The local community is fine with this. This is known. But anyways, we are not operating at a professional 5 nines level. And this is a challenge, or this creates a significant problem for us because we've talked to a number of small telcos in the United States, and they said, hey, no one likes paying $5 million for a package. We saw this open source package. What's the story? And they need rock hard stability before they can start migrating over. And to be clear, the FCC doesn't fool around with these requirements. People can and sometimes do go to prison for this type of stuff. So there's interests, but we need to keep building towards stability. This is hard to do with extreme heterogeneity in handsets. And this provides one of our first kind of open research question thrusts, which is, can we use techniques from software engineering, programming languages, formal verification? Because there are fields that I'm not familiar with as a network engineer in how to make something that is guaranteed never to crash. So this is one incredibly interesting potential future research field, intersecting this with this complicated cellular network architecture. The next big set of ongoing work that we're driving towards is hooking up telecommunication services, specifically voice and SMS. I mentioned that they're powered simply by VoIP. The protocols are, stupid simple, they're well known. many open source implementations exist, and what we found is no matter how hard we try, we cannot convince a phone to start speaking VoLTE with one of our VoIP servers. So this was at first, what are we doing wrong? Oh wait, we're looking at PCAPs. I think we're doing everything right. This has led us on the last year through a really interesting wild goose chase. It led to us installing open source software onto phones. It led to us rooting phones. And one of the first things we found is that aside from the major incumbents, you know, Telefonica, Verizon, so on and so forth, no phone supports, no network has been able to get a phone to make a VoLTE call on it. The second finding that we found, this was us in our lab, we started rooting a phone, we started really digging through it, and we found what appears to be a whitelist of networks that are allowed to support VoLTE on or not. Per FCTC, because these phones are unlocked, this is potentially illegal, and we're trying to investigate if this is actually the case, that there's a whitelist or not. A third finding, when we started really cracking the phone apart and looking into its interfaces and just really trying to wirecap all the traffic, was that we're not even sure what interface it's sending the VoLTE traffic on. I was trying for about a month to take a PCAP of a VoLTE call just over Verizon's network. This is me already having rooted and reflashed the phone's firmware. And there somehow must be some sort of hidden device interface because I wasn't able to find the traffic. Point is, fruitful research that is also very painful is underway, and we hope to have something out soon saying we hooked it up and this is what's going on, and there's a bunch of roadblocks that really seem to be intended to keep us stumbling in the dark. Okay, so these are our current ongoing engineering efforts, but there's other future research that is potentially fruitful as well that I want to mention to kind of wrap this up. First off, I mentioned that at a protocol level, we're still using the same VoIP codecs, we're still using SIP to set up phone calls. VoLTE, from a protocol perspective, could be considered identical to Skype or WhatsApp. And if you dig a bit deeper, there's two key differences. First off, in a phone network, yeah, it's voice over IP, but it's giving it priority. It's giving it a high quality of service. The second key difference is that you pay up price per bit markup of over 1,000% for this quality of service markup. This is to say, if you compare the cost of a VoIP call in terms of bits, and you compare it to the cheapest price per minute plan you can find. So this opens up a wide range of questions. The biggest one being, is it worth it? We're currently trying to spin up a way to conduct a performance comparison, kind of an apples to apples. What is the quality of service? How hard does it degrade? What's the average quality of a WhatsApp call? So is there a difference? Is it worth 1,000% markup? Question two is, because we're talking about a network prioritizing traffic to its own servers and services that it provides, there's kind of a curious question of, how does this intersect with net neutrality? Is this a net neutrality violation? In an IP world, now that telecoms are heading this way, the tempting answer is yes. And we'd like to see more discourse and dialogue on this front. We've been kind of working with the Tech Policy Lab to this effect. Question three is simply, when we talk about phone calls, when we talk about physical circuits, virtual circuits, it's just revisiting circuits and datagrams all over again. This is fascinating, just back to the classic network architecture discussions that people have been having since Vint Cerf in '72. There's also future work available on hybrid network architectures, which is to say, when you see the LTE signaling, control signaling has a tight time bound, and 5G signaling is going to be even tighter. This is obviously not a problem if you're a Verizon and you control the entire network, all the cables, all the fiber, all the backhaul. But as things continue to open and they continue to open source, there's going to be a wide range of other designs. Can we see cloud-based core networks? Can we run a 5G or an LTE network over the public internet, or will the time variance be too high for some of the control and security signaling? Does that question change if you're in a place like Seattle with like fiber trunks versus geosynchronous or low Earth orbit satellite backhaul? Can you run a 5G network over a geosynchronous satellite? Clearly not. The latency is way too high. But low Earth orbit satellites advertise really tight, low latency bands. Can we run 5G over LEO? This has yet to be demonstrated and or seen once both of these technologies get off the ground. And the question of this doesn't mean you're dead in the water, because this also brings other questions of co-location. Should we take the software network and co-locate it with the towers? Should we keep it in the cloud? Should there be hybrid models where you have some of the signaling is bound to the tower and other signaling can be kept back at a public cloud somewhere? So as open source cell networks mature, you're going to see a large range of hybrid networks and hopefully more interesting and kind of creative designs along these fronts. To this point, our lab has been exploring alternate security models, which is to say, in LTE, authentication is bidirectional, which means that the phone uses one key to authenticate the network uses another one to authenticate the phone. These keys are separate, they're symmetric, but can we explore things like a PKI? Can we find some way to bypass this and provide emergency connectivity, which is to say, we know that you can't authenticate me, I'm a network you've never seen before, but come on in, we'll give you the internet access. And note that in the telecom world, this is considered insecure. This is how the stingrays work to snoop phone traffic. But in an internet world, do we even need strong link security? Because we're already using end-to-end encryption. Most IP networks are not secured. The upstream sure as heck isn't secured because it's who knows who's running your backhaul. And so does a lot of the security architecture of cellular networks. It's starting to feel a bit outdated in terms of end-to-end encryption. And finally, we often collaborate with the Tech Policy Lab at UW. And when we talk about open source cell networks, regulations have been and continue to be a primary blocker in many ways that I've kind of alluded to over the course of this talk. In terms of spectrum licensing, the regime is starting to change. We're seeing use it or share it license is CBRS in 3.65 gigahertz. We've been seeing a bunch of tribal networks have just received licenses in the educational broadband spectrum, that's 2.5 gigahertz. LTE unlicensed has been standardized in the unlicensed band, so you can run LTE in 5 gigahertz without having to talk to anyone. There's some of the other questions that I've already mentioned with respect to net neutrality. How does that affect things like VoLTE? What's going on with VoLTE and so-called unlocked handsets? These are things that we're trying to explore and then trying to collaborate with the legal team on. And then finally, there's a huge question that has been kind of danced around throughout this talk, which is, what is an ISP versus a telecom? ISPs are best efforts. Telecoms have a lot of requirements, from lawful intercept to the 5 nines uptime that I mentioned. But in a world where telecom networks are IP based, there's not as much of a clear answer anymore. What I built in Papua, a cellular network to handsets that only provides internet traffic, we could be argued either way. There's obviously a lot of implications for this, and I think that we're starting to see the cracks in which these concepts are starting to become muddied, and we're going to see a lot more of that in the future. And so it's a really exciting time to be working in this space, and I hope you check out our code. I hope you run some of this stuff. I'm available here in the chat and to answer any questions. And thank you so much for listening to this talk, and please just reach out with any questions.